Now I think we can start. So my apologies for my apologies in advance, and we didn't have a screen for the class yet. Let me put the screen. Today we are going to go to Minimax. We'll be going through it relatively slowly. And the reason I wanted to apologize in advance is that the slides will cover the theory, but on the practical examples. And the reason is very simple, because I didn't have time to finish the slides. That's also why we're starting 5 minutes late. I was trying to finish the slides right before the class. Unfortunately, those slides usually take like 3 to 4 hours to finish. So this week, just didn't have time. That, my apologies. But we do have all the theory covered, and I'll add to the slides as soon as I have time. But also we have today we will have a interesting test exercise if you want. I mean, okay, we will get there as we go. There will be something interesting there. Okay, so what is today's topic? Today's topic is Minimax Optimization. It is interesting area of optimization. It is interesting in a sense that, first of all, it's not something that you, how should I put it? It's not something that you would naturally see as a part of curricular as we experienced it so far. So far we kind of went from tool to tool, right? We went, linear algebra was all about how we can use SVD, more or less, right? Then we, least squares, etc. Then we went to how we can use QP, LP, SOCP, SDP, how we can use mixed integer. All of this was around tools. So we did see some examples, right? If you remember ellipsoids, whereas the lecture on ellipsoids was kind of how you can use SDP to talk about ellipsoids. That was, pretty useful. Didn't have to do with SDP directly. It was just kind of how you can do it. Big M, if you remember last lecture, was also something how you can use ideas that you learned to do particular stuff. By the way, let me know if something is wrong, because sometimes I mess up my setup. So, okay, Big M was like this, and the Chebyshev center of polygon was like this. Center of linear inequalities was like this. Okay. Now, today we are going to get one more of those, and this is going to be slightly unusual. So today we are going to experience a class of problems which can be solved using tools that you already know. And those tools are not going to be anything new, but the class of problems is going to be completely different from what you saw before, both in, in the field of the problem and also in the formulation. So let us go directly into the problem. So Minimax problems. So consider the example on the slides. So let's say you want to find smallest x in R, so a scalar, okay, such that x plus y big or equal to 1, where y, its absolute value, is less than or equal to 2. Y is what is y? Is it a scalar vector matrix? What?
It's like a scale.
Yep, of course, right? Because you addition only defined between the same size operators. Good. So here you can see that y is supposed to be less than or equal to 2, right? So what are the scenarios? So y can be equal to 0, can be equal to 1, -1, -2, 2, -1/2, etc. You don't know what y is, and it's not decision variable. It's just in this case, it is just something that you don't know, but you know that it is bounded. So this boundedness is kind of allows you to consider worst case scenarios. And that is what this problem is all about. You want to find worst case scenario. In this case, worst case scenario is if y is equal to -2, right? If y is equal to -2, it is the same as saying that x has to be big or equal to 3, correct? Right? You just put y to the other side. And you wanted smallest possible x, and x has to be bigger than or equal to 3 in this case. But y could also be 2, right? What if y is equal to 2? Then x could have been bigger or equal to than -1, right? That would be much smaller x. Instead of 3, which is the answer, you would have had -1, also the answer. Can you choose to have x equal to -1? Well, you shouldn't. And the reason is because you don't know what y is. You can hope it is the most opportune number. But in engineering practice, you would usually, instead of hoping something is the best it could be, you'd prefer to be prepared for it to be the worst it could be, right? Right. So think about it as a very familiar example, elevator design. You probably noticed some elevators tell you that the total mass of passengers shouldn't exceed, like, let's say, 1,000 kilograms. Did you see it? Yep. So that means that the elevator was designed to handle this mass. What do you expect would happen if you put like 1,100 kilograms in it? Yeah, I mean, it would still work, but also it definitely wouldn't like break, right? Yeah, it wouldn't go up because of the sensors, but it's not going to break. That's an important point. In this type of problems, what I want to say is engineers who designed the elevator probably considered some brackets. Like they would say, okay, what if people exceed our, caution sort of like margin? What if they, instead of putting like 1,000 kilograms, they put 2,000 kilograms? And it should still work. So instead of hoping that it will be no more than 1,000 kilograms, they would actually consider worst case scenarios, right? That's kind of how engineering works. All right. So in a sense, this is called Minimax optimization. It's not exactly Minimax optimization. At least if you go to like Wikipedia definition, you would find that Minimax is the problem without constraints. It's just a cost function where you say, okay, minimize me a function of variables x and y, where x you can choose and y would be the worst case scenario. But here we'll kind of get like constraint minimax. And that's what I'm going to teach this whole time. Constraint minimax. So what you want to do is in this class is to make sure constraints hold. Instead of you thinking about cost. We are not going to think about costs this whole class. Minimax optimization. So you can also think about it as a game theory. Have you heard of game theory? Studied game theory or even like self-study? No? So game theory is basically, how is it different from optimization? Well, I mean, you can imagine, let's say your game is to go from point A to point B. Then it is just optimization, right? Find a path from point A to point B, right? Smallest possible path, whatever, optimization. Well, game theory is different from optimization in that it is played by two people or more. And the theory comes where, like, why is it like a big deal? Why is it different? Yeah, hello. Why is it different from like optimization? Well, your opponent would want to have the best possible move for them, which would probably be the worst possible move for you, right? So you would have two agents, and each of them take action, and the action of one agent is supposed to be bring them benefits, which is a detriment for you. So in this case, you can imagine that your opponent is y and you are x, and you have to work with the problem statement where you want to minimize x, but your opponent wants to maximize x, for example. So this would be a game theory kind of like context. Of course, in robotics, we don't really, we're kind of like far away from game theory in a sense, unless you do some like interactive stuff. But usually we are pretty far away from game theory. However, that is not, that is just, that's just how we feel. It's not really, we're not really far away from mathematics of game theory. Why? Well, for example, consider your quadrotor that moves between buildings. Your opponent in this case is just, for example, model of your wind, which is random, right? And it's not really an opponent, right? It's just a random process. But what you want to assure is that your quadrotor can still go from point A to point B. And you want it to happen under any circumstances. So whatever wind does to you, you still would want to be able to go from point A to point B. That you can consider as a game theory. You would want to say, okay, at this point in time, I decided to, have torque in this particular direction. And the wind can do whatever it wants because it's not, it's not bound by dynamics. If it was a dynamical process, which you could actually simulate, you don't have to invoke any game theory. You just say, okay, there are states, there are dynamics, we will simulate forward. No, but wind is not modeled by dynamics. I mean, maybe in general case it does, but it's like not in any realistic control scenario. So I'd say, okay, what is the worst thing that wind can do to me? And then you apply it, and you'd say, okay, I still want to be able to survive. So that's kind of like how in robotics you can do game theory. If you do autonomous driving, what is the worst case scenario other drivers can do on the road, right? I mean, of course, you can model their behavior more or less, but they will deviate, right? Sometime a person will just aggressively change lanes or speed up or slow down without any reason. And you would want your car to be able to still handle, right? So game theory. And I want to emphasize that what we are going to see in the following next slides is a way to solve very simple version of this adversarial like optimization, if you want. Very simple version, but okay, good. I personally found it very helpful for me in my studies. So that's kind of like the reason why I put the whole lecture here on it. All right. Now, here's a very simple problem still. Notice the problem formulation. I write it as mean over x, max over y. Why do I write it this way? Just to indicate that x is a decision that you take, and you want to minimize the cost function over it. Max is not a decision variable. It is your opponent, if you want. It's something that would get you in trouble. And you notice y only appears in constraints. Maybe it's abuse of notation, I don't know, but I think it is clear. Basically, what we say here is that y can be anything in this circle P. Notice that constraints on y it is bounded. And that is very typical constraints. In fact, today we are only going to consider this type of bounds. It's possible to consider different ones, but we'll only consider those today. Okay. What is the situation here? Our situation is very simple. You have two components, two scalars. One scalar is this guy, x times s, c, x times c. And second scalar is y times d, scalar products in both cases. S times c times x is whatever, depends on our choice of x. D times y depends on what our opponent will choose as y. And it will be worst case for us, whatever we choose for x. In this case, actually, we can say what worst case scenario is. Oh, it is when y is collinear with D. Why? Well, this constraint says it should be less than or equal to H, right? Should be less than or equal to H. Cool. Let me write it on the blackboard. So basically, we can imagine a number line, and here's H. So by the way, can we? Yeah, we can see it. So 0. Well, what does D times Y do? Well, if it is positive, it will get us a new boundary, which is H minus D times Y. So our domain will be only this part. This is not going to be in our domain. That is what's going on with this constraint. Okay, good. So D times Y should be positive. If it is negative, it's only making it better for us. But no, so say it is positive. By the way, here is an important detail. I'm assuming the origin is here, and that yeah, I mean, here is a problem with this problem statement. We'll need to think about. Okay, we'll go here in a second after we finish our initial discussion. The question where the origin is very important here. Okay, but anyway, let's first just do it in a simple way. So we have this constraint, and if D times Y is positive, our domain shrinks, right? That's pretty much the whole point of the situation. If H is positive and D times Y is positive, our domain is definitely shrinking. I mean, if H is negative, it does the same thing. Okay, now, what now? We can say that we know the direction of Y. Direction of Y has to be collinear with D. Why do I say that? Oh, because if it is not collinear, it's just going to have a smaller size, right? The length of Y is just is P at most. We can choose Y to be smaller. That is, we can choose it to not be collinear. But all of those actions will only make it this whole product smaller. So the worst case scenario is always when they are collinear, those two vectors, and when Y has length P. That is just the biggest this product can get. If we want sign to be different, we just make them collinear, but point in the different directions. But so we can do sign change, but they're definitely going to be collinear. There's absolutely no reason why in this scenario they would want to be not collinear. Okay. So how do we write collinear vectors? Well, it's, Y would be equal to D, but divided by norm of D, right? Except its length, this is a unit vector. Length has to be multiplied by P. So that's the story. Now, let us substitute this thing back into this constraint. Our constraint is, remember, Cx plus dy less than or equal to H. So let us substitute this thing there. Let me see where I should write. Wait, let me just write this here. Is this acceptable? Yeah, it is acceptable. Okay, so we'll substitute here. What we'll get is and notice actually, this is just a norm squared, right? I just substituted this thing here, and I got here a norm squared. So I can rewrite it. Let me rewrite it here. It will be the same as Cx plus D, norm squared divided by norm. would be just norm, right? So less than or equal to h, or cx less than or equal to h minus d, which is, oh, by the way, I forgot p, right? I forgot p. Here p was here, and here I forgot it, times p, right? D times p. And by the way, yeah, so this is the story. Yep, this is the story. So you would have this kind of constraint. What is this constraint? Is it linear, SOCP, SDP, quadratic? Is it SOCP? Why? Absolute value of D, but D is not decision variable. That's a very important distinction. So it's linear. Yep. I mean, that's the reason why I asked this question. That's exactly because I wanted you to see that this looks like a SOCP, but it's not. But you know, it's, yep. I'm going to do it the whole class, so be prepared. This is just a scalar. It's just nothing, just scalar. It doesn't change anything. So this is a linear constraint. It's very, very, very simple. So you can see this problem is still quadratic. Any questions? Can I answer? No? So you can see this is a quadratic problem. This becomes quadratic problem. All right. Yep. Yep. All right. Now, consider this, yeah, before we go, let me go back. Now, what is the catch? Here, there is a ton of catches, but, let's just consider some of them. So if 0 is here, and our worst case scenario is this, and our best case scenario is this, does it actually make any difference? It actually doesn't. That's the point. Actually doesn't. Actually, worst case scenario, best case scenario are the same scenario. Answer is exactly the same. If 0 was not here, but let's say, when I say, when I say 0, by the way, it's now let me be even more careful. So 0 here, what does it refer to? Oh, it refers to, like this equation, basically. So let's again consider this scenario. It is here, right? This is this scenario, like this situation. So this domain that is written here is described by this equation. Okay. So 0 is inside this domain. What does it mean? It means that if x is equal to 0, from this it follows that c times 0 is in the domain. Or write it like this. Okay. If 0 is here. Okay. Now imagine that 0 is actually here, and all of this is just negative. Okay. Here's a here's a worst case scenario. Here's a best case scenario, but 0 is still outside of all of those scenarios. Well, in this situation, it's not going to be true. So so in this scenario, if it was true, then that's the answer, but it is not. So the answer is going to be on the boundary, not in the point x equal to 0, because x equal to 0 is just a global minimum of unconstrained problem, and our constraints actually didn't change the solution, which is perfectly normal. But it just implies that whatever game we played with our minimax didn't matter at all. But imagine that 0 is here, then it does matter. Best case scenario will give us very close solution to the 0. Worst case scenario, much worse solution. And we'll have to use this one. So that is the story. And notice, in both cases, still the worst case scenario is still the furthest to the left, regardless of where 0 is. So, okay. So those are the catches. I mean, you need to think about those things carefully, but there are sources of error here, which can come, for example, from the fact that you actually have two scenarios and you don't know which one is the worst case and which is the best case. You need to be careful about that kind of stuff. Okay, good. I mean, you don't know before you thought about it. When you think about it, you will know. Okay, good. Now let's consider a different one. Notice we have a different cost function, x minus x desired. That way you don't have to think where your 0 is. You just have to think where your x desired is. You want to be as close to it as possible. And your constraint is now quadratic. Notice expression 2, quadratic constraints. So what is worst case scenario there? For worst case scenario, it is written down on the slide. Worst case scenario there is when y is aligned with x dx, right? You have dx and y is aligned with. But you would have to normalize to alignment. When you talk about alignment, you need to talk about unit vectors, not vectors, right? So you have to do this kind of stuff. And norm is still p at most. So this is a scenario that you get. Now let us substitute back here dx, right? That is the same as x transpose d transpose dx dx p. And notice this is again norm squared. This is again nothing else but the product of the vectors itself. So what you get here is norm dx times p. And that is what we get with, you see it in the slide, expression 3. That is absolutely typical for Minimax. And that is pretty much one of the most important pieces of today. It's very simple, but it is important. This type of discussion. You say, what is the worst case scenario for this function? Well, it is this. How do you know? Because alignment and length. Just to give you a little bit more interest, if you are going to study adaptive control, for example, you would find this whole thing there. It is in the derivation of margins. There are, a few scientists who developed adaptive control or slightly mode control, where they talk about margins of stability in terms of those variables. And those margins comes from worst case scenarios discussed exactly in this way. So it's not just Minimax, it's also just a derivation of formulas. So that is good. And actually that's a very typical way of deriving stuff in control theory. Anyway. Okay, good. Now we can see that our problem becomes expression 4. That is SOCP. Because this constraint is actually SOCP because x is inside the norm. So it is an SOCP constraint. Good. And we know how to solve SOCP. So now we can solve actually this type of problems. Expression 2, we can solve it. We just need to cast it as SOCP, and we know how to do it. That is very interesting. Also, we can generalize it even a little bit more. So let me consider this type of problem, expression 5. Expression 5 is different because our constraint now has more variables. We have x, let me write it the same way as on the slides. We have y minus a. d x minus b. It just happens that they have centers, if you want. If you can think about it as, the center, this is a variable, the center is a variable. I mean, the word center doesn't actually maybe makes a lot of sense, but, it, I don't know. Basically, what you can think about is there is some variable that you could have, described. Okay, let me not go into rabbit hole, but basically, it is pretty typical, right? You have a variable in you, instead of expressing it in terms of the variable, you want to express it in terms of distance from its typical value. Okay, like control error. You remember that, let's say we have x desired, and we have control error, which is x minus x desired. You can notice that, this E has this form. Okay, we want to punish E, but instead we write it in terms of original variables. It's like all there is to it. Okay. Now, by the way, was it even visible? It was visible. Okay. What can we do with it? Well, I mean, that is kind of trivial. We do exactly the same thing, except first step is to break the brackets here. That is, nothing spectacular, but it is just a useful trick. You don't really want to think about this thing, because it's not something that you know the length of. You don't know the length of this one, but you know the length of this one. And this is actually completely harmless. It is something, what is it? Oh, it's just a linear function of x. We can do whatever we want with it. All right, so, and with this, we already know how to deal with. What is worst case scenario for this function? Well, when y is, collinear with x minus b, which would happen when this is true, times p. Where does the p come from? Well, from, norm of y being restricted. So we know how to deal with this. Let me substitute back. And I'll write it as x minus b transpose d x minus b divided by dx minus b p minus a transpose t x minus b less than or equal to h. Great. And notice this is again our familiar norm squared. Right, this is a norm squared again. So we can write it, let me write it here maybe, as dx minus b norm p less than or equal to, I will put everything here to the right hand side, be h plus a transpose d x minus b. This is still SOCP. Why? Well, general form of SOCP, if you remember, is something like, well, let me write it more, I think it was written like this. So like here is the D, all of this is C, this is A, and B is A times B. So SOCP, right? It's clear. I don't need to derive it, right? Okay. So this is SOCP, and that is exactly what we wanted. So you see expression number 8 is what was written on the blackboard. Then we go 9 and 10 is our final one. SOCP constraint. Great. We just managed to solve this problem, and it was no harder than the previous one. But now we can use those centers. That's very nice. I mean, those centers are going to be very nice. Notice, difficulty goes up in terms of how much clutter we accumulate, but it's not really, still a CCP. It's just a matter of substitutions. Okay. Now, a final problem, looks bigger, but it's actually not more difficult. Okay. Also, here, I would, I'm not going to do anything with it, but I just want to suggest you to think, can you choose worst case scenarios here? Remember, with absolute value, you could choose worst case scenario. You would say smaller or bigger, depending on that, you would have a worst case scenario. Here, can you choose worst case scenarios? And could you really choose it before? That is two open questions. I would just leave it with you. But just maybe just as a piece that you can think about, I would like to say, let's say this is scenario 1, scenario 2. Scenario 1, scenario 2. You don't know where your origin is. You don't know where your minimum is. Your minimum can be here, or your minimum can be here. You don't know where it is. Okay. So, you would think, right? What I want you to think about here is this is actually, this is actually not a, this axis is not x, like it isn't. That is some scale of variable s. What is this variable? Well, it's just constraint. That's a value that your function that represents your constraint, like this function, takes. It has nothing to do with your x or with your cost. Your cost is a separate cost function. Maybe your cost function exists here, like, and who knows what values it takes. Okay, so, but what you do know is the sign of your constraint. That you do know, and we always assume it is less than or equal to. So your scenario number 1 here would give you this type of domain, and scenario number 2 will give you this type of domain. And maybe you can think about, which one is worse. Can S1 be worse than S2? Interesting question, right? So think about it. Can S1 be worse, or can S2 be worse than S1? Right? Like, regardless of where your cost is. Can you imagine a scenario where having a bigger domain would be worse than having a smaller domain? And it is always this. It's always bigger or smaller domain, because this is a scalar. Just always scalar, because this is a scalar equation. It cannot be anything but scalar. It's quadratic form. They produce scalar output. So, can small domain be better than bigger domain? That's, but think about it. Like, just ask yourself, make sure you are confident in saying that it cannot be. Okay, good. Now, that is good. We solved 2 types of problems. Now, let me consider first relatively challenging one. I mean, they were all challenging conceptually, but this one will require more tools, slightly more. Okay, so my strategy, first of all, what is the difference? Well, the difference is very simple. Now, y is constrained in this fashion. H, y plus f is less than or equal to p. So that is the difference. What does it actually mean? Well, previously, when we had this type of constraint, our domain was a circle for y. Y was a circle, or a disk, right? Interior of a circle. And why, by the way, it is not a, why is it a 2-dimensional? I mean, it could be like 10-dimensional, right? But didn't we just discuss lines? So why is this suddenly dimension shot up into something bigger than 1 dimension?
I think because in the case of S, we were discussing the projections.
Yep, exactly. I mean, that's as correct as the answer you can get. We projected here y, which is an n-dimensional variable, onto this line. Because we have one constraint, but our y can be n-dimensional. That's the story. Okay. By the way, does y have to be, well, let's say x is in Rn. Does y have to be in Rn? Does y have to be in Rn? Oh, the answer is not. It doesn't. Why? Well, because y and x are never directly multiplied. They multiplied via matrix D and stuff. So, but you know, often you would expect them to be on the same dimensions, but not always. But if they're not at the same dimensions, means D is not invertible. So your algorithm better not expect D to be invertible. And sometimes it is very convenient to have them invertible. So, okay, good. Now, what does this mean? Well, this means that your domain is actually, you know, first of all, shifted by f, and then is ellipsoidal. So your domain is actually something like this. That is your y. Sounds good? I mean, by now you're familiar with ellipsoids, so you know, no surprise. Okay, great. Now, I would suggest a change of variables here. Or as you know, on the blackboard, we have this change of variables. So why do we want this change of variables? Well, the strategy dealing with this type of constraints is to get back to what we know. We know how to deal with this type of constraints. That's where we are heading. I would just change variables until I get exactly this constraint. So this instantly gets me this constraint that I know. Like we instantly got here. But now we need to reformulate everything in terms of v rather than y. And you know, from this it is clear that we have h to the power of -1 v minus, I believe, right? Yep. -1f. Is that correct? Yep, it's correct. Any mistakes? No. Cool. So this is something we can substitute now to our equation. So our equation, you remember, it was, I mean, I don't want to rewrite it. It is on the equation 12. We want to substitute y there. And you remember we wanted to work with this equation. D times x minus b plus a d x minus b. We wanted to work with this one. So let me put this whole thing there. So you would get v minus f transpose h to the power minus t, or h inverse transpose d x minus b plus a d x minus b. So this is what we get. Expression 15, I believe. Yep. Now, okay, expression 15. Cool. Now let me gather v in one spot. Any question? I mean, just stop me and ask me questions.
Is it supposed to be minus 80?
Over here?
No, no, plus.
Here, a transpose d times x minus b. Here, minus, right? Yep, thank you. It's a good catch. Minus, minus. Good. So let me collect v in front of just, you know, so we'll just have v times something and everything else in the second bracket. So it will be v times this whole thing. Minus, and here we have like f plus a, right? Except it will be f times h plus f plus a. So it will be f, let me write it correctly, h minus t f plus a d x minus b. This is not pretty. Let us do the following. We can multiply it by h and h inverse. Or we can put h inverse out of the brackets if you want. Let me put it out of the brackets. If we put it out of the brackets, it would go here, same as in this case. So it would get h d x minus b minus, here it would be ha plus f h t d x minus b. Why is this here? I mean, it's just let's open the brackets again. We'll get h times h inverse go away. Yeah, by the way, where did transpose go? Here it should be transpose, it should be -1. Where, yeah, transpose obviously is, you know, this -1. Yep. So it's, this whole thing should be transposed. So this h will be destroyed by this h, and this guy will get his inverse. Okay, good. Now, what we observe here is that this guy is just our new matrix, and no, this is just our new A, right? I don't know how I denote it, but let's see. Let me denote this M and this as G. Then we can see that our equation can be rewritten as V transpose M x minus B minus G transpose M x minus B. And that is actually what we know how to solve. We just solved it previously. How? Well, V would have to be aligned with this vector, which is going to get us, you know, P times norm of this guy, and that is SOCP. That's we know how to solve. Expression 21, that is the answer. So expression 21 is exactly the same as problem type 2 that we already solved. I mean, those types are just made up thing. It's only for this class. You don't have to memorize any of those formulas. You just want to understand my way of thinking and apply it. So here, my strategy was go to problems that we know how to solve. What's the difference? Only this. This was the problem. So change variables, then rearrange. That's all. And previous problem, you remember, it was, you know, just problem type 2. Let me go back. How did we solve this one? Well, we just you know, did the same as with type 1. We just you know, observed what is the worst case scenario, and we went for it. So type 1, type 2 are the same, and type 3 can be made into type 2. So that is, you know, you see the pattern here. Okay. Final one is now here is the, you know, experiment for today's lecture. So I don't know, it's a good experiment or not, we'll try to see. So this problem here, expression 22, I don't provide any solution for it. I just give it to you. And I would award extra points, let's say 5, to whoever, like, you know, let's say 3 people who would submit me their clearly independently made solutions, clearly independently made. If they are like clearly not independently made, only the first one gets something. And you can submit them as a pull request to the Git repository. You can submit PDF, but if you submit or collab notebooks, both are acceptable. I mean, I just want a derivation. Sorry, you also can do Markdown. You know how Markdown works, right? Okay, probably Markdown is a preferable option because PDFs are a pain to, you know, to have. in your history. Although, you know, you feel free, you submit PDF if you want, like whatever, do whatever, it doesn't matter. But you know, try to solve it on your own. You notice there is a catch, those linear terms. We don't know how to deal with it. It's a little bit strange, but the ideas of worst case scenarios are still completely there. So, but by the way, I would encourage you to, instead of rushing and submitting fast, it's never worked. Think carefully and present your arguments very clearly. There is much higher chances that I will give like 5 people's 5 points than I would give one person with a half-baked, you know, not convincing arguments, anything. So, I mean, I break my own rules all the time, but only when I see good work done. So, just an experiment. We'll see how it goes. So, expression 22, prove it. I expect a proof of the style of today's lecture. No, just get it to the same structure as a problem you already know, or just solve it directly. Anything will work. Okay. Now, questions. Not about this one, about what previously was discussed. What we did get for what? From here? How we got from here to here? From here to here. So let's consider this a little bit more carefully. So let's write this thing. Sorry, let's write this out. Only this one, only this part, okay? So this is the same as saying F trans, here there is a transpose, it is transposes here. This is the same as F transpose H minus T plus A transpose times M. Okay. Now, let me multiply it by, so we can write it this way, but we can also put here like H inverse transpose them, because this is identity. We can just, you know, we can put identity here and break it as H transpose and H transpose inverse. Standard practice, right? By the way, here it was D, right? It was D. Okay, now let me put this into the brackets here. I guess I didn't have to write it like this. Let me just keep it as -1 F plus A and all of this transposed. Let me put this inside the brackets. When I put it inside the brackets, what will happen is transpose will go away, and instead of being on the left, or on the right, it's going to be on the left, right? That's how we put something under transpose. You know, just remember that this is the same as this, right? So by the same logic, this transpose will have to go on the left, right? So what you would have is, let me write it so people can see, online can see as well. I'll write it here. Can we see? No, we cannot see. Well, let me get rid of this. So what we'll have is H inverse F plus HA transpose H minus TD. And this is just identity matrix now. So from that we get F plus HA transpose minus TD. So this is the process. And notice this trick is very useful when you have at least, you know, either you know that H is invertible. If H is invertible, you can do it all the time. Or you know that this vector lies inside the whatever column space or row space. I mean, depending on how you treat your matrix inside one of those subspaces of this matrix. So, but if you think about subspaces, be careful, because in this case, for example, you have no idea where this guy lies, so shouldn't really expect it to lie inside like subspaces. For some problems you can, but you should be careful. But this one is invertible. How do I know it is invertible? Well, if it is not invertible, what actually happens here? Well, actually, this is no longer ellipsoid. There's actually a line. So it drops a dimension. So what you should do is just change variables, just introduce new variables where this is dimension, lower dimension, like it has one less dimension. And in this one less dimension, it is ellipsoid. Just project it into a small dimensional subspace, because there is absolutely no point in saying that this guy, for example, let's say you have two parameters and you say 0, 0, 0, 1 times x is less than or equal to 1. Well, this is pointless, because what you're saying is that 0 squared plus x2 squared is less than or equal to 1. Well, that is the same as saying that x2 is less than or equal to 1, right? Just drop the dimensionality. And here is a bona fide circle or ellipsoid. Here is just nonsense. I mean, it's not nonsense. It's just it's still the same. I mean, when I say this circle, what I mean is it's like one-dimensional thing, right? That's what it is. And here it is exactly the same thing. It's just in 2 dimensions. But why presented in 2 dimensions? That's how you get uninvertible matrices. And why would you want that? So, by the way, it's very interesting, right? You would say, but okay, it's like good, like, sure, professor, but why? How should I do it? Like, how do I project it? This is very easy to say, just project into a low dimensional space. But how? Well, here's an example. Like, just tell me how. Sounds very interesting. But indeed, how do we do it? Well, let me just show you how we can do it. That's content you don't need any extra knowledge for, because you already know how to do it. It's just I just need to connect it for you. Or maybe some of you can tell me, if you want to. Stop me at any point if you want to. So let's say you have H, which is you suspect doesn't have one dimensionality. So it's H is in the Rn times n, but rank of H is, let's say, a minus 1. Okay. So what you can do is to say, okay, what is a column space of H? Oh, it's something like some base. There is some basis in the column space. How do you get this column space? Well, by calling orth in MATLAB or Python, or just SVD and getting the first n columns. Good. What next? Well, next, let us just project into this column space. And we want to change coordinates. So basically what we want to say is our original equation is something like this, right? Let's just for simplicity put it like this. Here is our original equation. Let us, and we know that y has to lie in the column space of H, right? Has it? Yeah, by the way, here we come to an interesting problem, and let me just spell it out. I think I slightly misled you. So the problem is, if H drops dimension, what actually means is not that this guy is going to become a line. That was my mistake. What does it mean? Can someone tell me? No, it's unbounded. There is a dimensionality. It means that if this is true, it means that null space of H is not trivial. So you have a null space basis. And if Y is in the null of H, it can take any length. So in fact, what happens is as your rank and as your determinant goes to 0 in one direction, your ellipsoid becomes something like this, and eventually it will become, instead of an ellipsoid, it will become a band. So it's still going to be circle. It's just a cylinder, infinitely long cylinder. That's what we're going to become. And that's actually not good because it's unbounded. And Minimax, not clear if it has a solution for a non-bounded problem. So that was my mistake here. So if H drops rank here, not good. But I still want to try to, analysis, right? So like not solution, just analysis. We can find that our problem statement was not good. When could it actually degenerate into line? Well, here, we can still do it, right? It will degenerate into the line if Y is in, some set, and the set is determined as set of all Y such that H. Let me make sure I don't say anything stupid. Yeah, it's set of all H Z plus, just say HZ, such that Z is less than or equal to P. So this is where it can degenerate. Does this make sense? What I'm saying is there's a unit disk. Unit disk can become stretched as an ellipsoid. And this ellipse now, if H has a rank, has a rank smaller than n, then this becomes, instead of ellipsoid, a line, right? Does it make sense? So it's still bounded. In this case, it has to be bounded because this set is bounded and this is just transformation of the set. In previous case, it could be unbounded because our constraint became degenerate. In this case, it will be the set itself becoming degenerate. Okay, now let's come back, say C is equal to column space of H. Well, what we have here is new coordinates. And we know pretty much that our, what do we know? What can we do here? What can we do here? Let's try to do it together because I'm just having a blank out. But it's clear that what we should do is express new variables in terms of this new set. I think. Suggestions on your part. So we know that Y is, any element, particular Y, can be represented as H times Z. That is, what it says pretty much. That Y is going to be something like this, and Z is. Okay, but we also know that it is the same as saying that Z is equal to C times zeta. We don't know how zeta is limited, but we can output anything that H outputs by using C. Okay, so that is something, and zeta is going to be correct size at least. like first instinct, at least that I would have, is to say zeta can be determined as C transpose, C transposed Y. So we can know what zeta is, but we know what Y is. So it is the same as C transpose H Z K C transpose HZ. And from that, we can try to find, and this matrix is now, what is this? Yeah, good. Now there is just one last element. So this matrix has the correct dimensions in this size, but we just need to somehow change that into a better representation. We need to change that into a better representation. Why? Because right now it is in the coordinates that are too big. What do I mean? It is, let's say, 3-dimensional, and our rank is 2. So H has null space. Let's denote it as N, and has a row space. What is going to happen? Yeah, so let's define that as equal to N times zeta is already taken. That's maybe unfortunate. Let's say, okay, N times alpha plus R times beta. So this is a null space. This actually doesn't do anything. It's a completely useless component of Z. So Z can take any, yes. So what I'm trying to solve is project basically the problem into lower dimensional space. So it redescribes the set in terms of a new matrix where the matrix is going to be instead of n by n, it's going to be like smaller, invertible. No, as a slides is irrelevant here. Basically, what we're actually trying to do is just to show you that kind of like the process of solving those types of problems on Blackboard, I guess, because it's definitely not educational content. It's like more of a let's try to solve it together content. I'm sorry, maybe I shouldn't do it. I mean, it's like, I don't know if I do more damage, psychological wise, or good. All right. Those are low dimensional basically. So it would have, so this component is not going to actually do anything, right? By the way, this is very interesting. So it's null space of H. So null space component of H is not going to affect Y. Yeah, but so it is completely useless for that to have this component because it's just going to make Y smaller. So it's going to, so that is actually going to always be of this form because null space component is useless. And we're playing the game where we take worst case scenarios. It's not worst case scenario, this is. All right, so now we know that we can rewrite zeta. Let me write it somewhere where people can see, maybe here. You can see here, right? Yep, you can. Can you? Yep. So zeta is going to be equal to C transpose H R beta. All right, now, here's the catch. What is beta? How do we find size of beta? Well, what is interesting, this is a orthonormal matrix. This doesn't change the norm. The norm of Z is the same as norm of R. Well, sorry, is the same as norm of beta. Why? Well, for a very simple reason, because that's orthonormal matrix. And so therefore, we know that beta is less than or equal to P. Okay, that is great. Should have, yeah, that is great. Now, now we have this matrix, which is this one has to be invertible because, like, you know, rank of this matrix has to be whatever rank of H was, but the size of this matrix is also the same as rank of H was. So this one is invertible. So we are happy. The only problem is, let's say we had our original constraints were something like, how do we rewrite it in terms of like zeta? Well, I guess we should use this one. So we would have zeta transpose C transpose D X less than or equal to H. Sounds just a little bit like cheating because C is not invertible. However, C is orthonormal. So we definitely know everything about its null space, etc. So yeah, we know how to do like inversions and whatnot. So, but in this case, at least you you know that this guy is inside ellipsoid. So, and the ellipsoid is determined by this matrix. And yeah, you have this non-square matrix here. So this is the process. This is how I would, I guess I would, you know, project into low dimensional space.
I have a question.
Yes.
Will the answer of the same problem, like this problem, will be the same as like lowering the dimension and projecting and getting the, will we get the same results in both cases?
Yeah, I mean, of course. No, if our original problem was this, but with degenerate matrix, this formulation is just the same problem, but formulated in different variables. If it wasn't degenerate, both of those are identity matrices. Column space of full rank matrix is identity. Row space is identity. So this identity is this identity. The beta is just a new name for our Z, and you know this is clearly just Y, right? So you see, it's like if it is not degenerate, we didn't actually change anything. So, yep. Why did we ignore null space? Because if Z has a null space component, it's going to be annihilated when you multiply it by H, because that's what null space does. So some part of Z, which is a limited resource, is going to be wasted. And the game we play here is that we've utilized all our resources to make things worse. So that would have to be utilized completely to make our constraints worse. And this is definitely not utilization. You understand, right? So that's why it wouldn't have this component, because it's just would be sub, not the worst case scenario, sub worse. Right? Any questions? Sorry about this random projection content, but it is good. It's like you remember subspaces. Though I'm not sure if this was super convincing. Okay. Now let me present you one example. Let me see time. Oh, do we have time or do we not? We don't. Okay, great. That is maybe a blessing because we still haven't reached the point where the slides abruptly end. And next time you will see slides not abruptly end, and they will actually continue, and you would have a proper lecture. That's good. So if I didn't tell you in advance that I didn't complete the slides today, you wouldn't know. And if I didn't record this thing on YouTube, it would be absolutely great. All right. Thank you, everyone. If you have questions, I will stop recording here and we'll discuss your project questions. I had a ton of them on my Telegram. Sorry, I didn't answer. So, all right. Bye-bye to online viewers.